Okay, so here are the mass spectra, the carbon-13 NMR spectra, and an IR spectra graphs for an unknown molecule, let's call it Y. Now what we're going to do is we're going to analyze the aspects of these different techniques, spectroscopic techniques, to identify what is the structure of this unknown molecule. So the top graph on the left, the mass spec one, let's look at that one first. Now what we can see here is, and this might be hard to see, but I'll circle it here. Here is the peak furthest to the right here. This is going to be our M plus peak, or the peak that forms when the molecule is put through the mass spec, but actually doesn't fragment, but has a charge of +1. So this is our M plus peak, and here it's 58 NZ, right, which is a measurement of the charge. How much charge there is per mass, right? So there's the mass is 58 for one charge, let's say. So what that means here is that because there is 58 ms peak here, okay, that's the one that's furthest to the right. This is M plus peak because it's at 58 mz. Then the molar mass of the original molecule must be 58 grams per mole. So that's the first bit of information we've found. Now, often the other peaks can be used to tell us something about the fragments that the molecule might break into, but these ones here are a bit bunched and it isn't clear what the fragments are. However, what we do know is that we cannot see any M plus 2 peaks to go with that M plus peak. So we can't see an M plus 2 peak, that is two peaks that are 2 units apart to the right that have a ratio of 1:1 if it was a bromine isomers, or 3:1 if it was chlorine isomers. Those are absent, so what we can definitively say is there's no chlorine or bromine in this molecule. Let's go on and have a look at the carbon-13 NMR graph. So this is measured in parts per million, ppm. Now what we have here is we have 3 peaks. Now what these 3 lines indicate, now what's happened here is the substance that the molecule's dissolved in, which is dichloroethane, I think, that is not shown on this graph. Sometimes it is, and it will be labeled as this is the molecule, the solute that the molecule is dissolved in. It's not on this graph, so we've just got the 3 peaks from the molecule. Now what that means is that there must, because there are 3 distinct peaks separate from each other peaks, we can say that there are 3 unique carbon environments. Now if we look more closely at where these peaks are, we can see that there is a peak at 62 parts per million. Now because it's at 62, okay, so we're going to think that that's very close to being in the range where the carbon environment is attached to an oxygen. The oxygen has shifted it further up the range here. So we're going to write that down. There's most likely a carbon-oxygen bond, usually between about 50 to 60 is a carbon-oxygen bond, but around there, around the 60. And then the other 2 here are within this range of, I guess, 100 to 140. Okay, now these 2 peaks are in the range we would expect from carbon environments that, so the 117 and 139, sorry, these are carbon environments that would be have a double bond attached to them. Now that doesn't mean there are 2 carbon double bonds. What it means is that there is a double bond, and each carbon that is involved in the double bond is in its own unique environment. Okay, so we found that information. So at least 3 unique carbon environments. We have a total molar mass of 58. But let's have a look at the IR graph and see if we've got any other information. So we have this broad peak here. Now we're going to exclude this peak just below 3000, which is caused by carbon to hydrogen stretching. But we have this broad peak here. Now this is between 31,000 here and 35,000, sorry, 3,100 and 3,500. And we can centimeter -1s. We can see that this peak, well, we know that this peak, then the shape of this peak, that is that particular blunt shape, originates from an O to H stretch when the OH is attached to a carbon but not a carboxylic acid. If it was attached to a carboxylic acid, then the actual peak is considerably more broad. Okay, so we know this has come from an alcohol group, so there must be a carbon bonded to an oxygen that is part of an alcohol group. We can see this other little peak here. Now, often a little peak here in this zone, around about 1600, indicates that there is a carbon-to-carbon double bond. It's from a carbon to double bond carbon stretch. And so here we're going to write down that we think this could be evidence that supports that there's a carbon double bond carbon. Now we have all of these other peaks to the right of 1500, but to the right of this graph is called the fingerprint region. That is that we can't use those peaks very well to identify exactly what the bend or stretch was happening, where it came from. But if we got this picture and we already had a picture of the unknown molecule, we could match them together and find out that it was the unknown molecule. So these peaks here are distinct for this molecule, but we can't use it if we don't know what the molecule is to determine it, anything under 1500, so we just ignore that. So if we bring all this together, what we're going to try and do is take information from two different graphs to solidify the functional groups or the carbons that are present. So, and if I was doing this for the spectroscopy achievement standard for NCEA at level 3, I would have to identify two aspects from each graph to pass, and then I would have to describe or explain those aspects too from each graph and identify a molecule to get a merit. So both the NMR, this graph here, and the IR both indicate that there is a carbon-oxygen bond. Now, the NMR does it by saying, well, there is a carbon-oxygen bond here, and the IR does it by saying, well, there's an OH functional group, an OH stretch, which means that the OH must be bonded to a carbon, so there must be a carbon-oxygen bond here. So this is me integrating, taking two bits of information to know for certain that there is a carbon-oxygen bond in this molecule. The second thing I can find out is from the carbon NMR, we can see that there is two unique carbons that are involved in a double bond, so there must be a double bond present in this molecule. And also, if we look at the IR, there is a peak here suggesting there is a double bond in the molecule. So I can be quite confident now that there is a double bond in the molecule, and remember, I also know that there is a single bond carbon to oxygen. The next thing I know is that there must be three unique carbons because there are three unique carbon environments. Now, because I know that there are at least three carbons and I know that there are two oxygens, I can add those up, and when I add two oxygens, that's 32, plus three carbons is 36. I get, wait a minute, let me do this again. One oxygen, because there's only one oxygen atom, plus three carbons. When I add that up, one oxygen plus 36 plus 16 equals 52. Okay, I get a molar mass of 52. Now, the molar mass of this molecule is 58, which means if I have three carbons and oxygen, I've got 6 more units to make up, and they can be made up by 6 hydrogens. So the molecule I'm going to draw has 3 carbons, 1 oxygen, and 6 hydrogens. And if I put all that together, I get the molecule here, 1-hydroxypropantuene. And this is my unknown molecule. It meets all the requirements. So 1, 2, 3 unique carbon environments. There is an OH joined to a carbon. Okay. The molar mass is 58. So I can be happy that this is the correct molecule. To make sure I got excellence for this in my explanation, I've included at least 2 aspects that I've integrated to explain this. Look out for the next explanation I do. Hopefully this has been helpful.